Solving acid-base problems, lecture number 23. So just like when we talked, first I discussed this idea of equilibrium. We sort of laid the foundation for what those equilibrium values were and then calculated concentrations from that. We're going to do that same sort of process here. Now the equilibriums that we're talking about are either acids or bases. So we can then define those equilibrium values and calculate them the same way, they're still equilibrium expressions, as we did here in this acid bases as we did before. So typically now, instead of then talking about the concentration of a product, we're typically going to find the pH value. That's the only thing. Remember that the pH is the negative log of the H plus concentration. Right? So our problem-solving approach is going to be very similar, in fact, the same as when we calculated equilibrium concentrations. We're going to write a balanced chemical equation, or equilibrium equation. Write the expression for our equilibrium constant. If it's an acid, we call it Ka. If it's a base, we call it Kb. If it's just an equilibrium, we call it Kc. The same process, same expression is going to exist. Define the changes from where we are initially to where we were going to be at equilibrium using a small value x, using the istable. Construct this value to figure out an equilibrium concentrations in terms of our initial concentrations and this change x. Put those equilibrium values into our equilibrium expression and solve for x. Right? Remembering that if possible we can use this assumption rule. If not, then we would use the quadratic equation. Remembering that the assumption applies if typically I try the assumption if the value of K, the equilibrium constant Ka or Kb, is more than 3 more orders of magnitude different than the initial concentration. So if our initial concentration is 0.1, we should try the assumption if the equilibrium expression has 10 to the minus 4 or smaller. Right? Then the assumption should work. Right? If we make the assumption, remember we have to write down that we're making the assumption and then go back and check that assumption to make sure that that value that we solve for x is less than 5% of our initial value. Same rules applied as when we had first introduced it. Right? Again, these brackets are going to represent the concentrations. And we're making several assumptions. One assumption that we're always making is that initial concentration of H3O plus, which should be about 1 times 10 to the minus 7th, is going to be much smaller than our eventual concentration that we have in these acid-base problems. Right? So that we can make this second assumption is possible here. Remember, if we make the second assumption, we need to write that assumption down and then go back and check to make sure that it is less than 5% of the initial value. We can also talk then about a new property in these expressions called the percent ionization. Right? So the percent ionization is the amount of ionized product, one of those ions in our product, divided by the initial concentration, or all the total concentration of our acid or base, times 100. So for a monoprotic acid, HA, the percent ionization is going to be the concentration of H plus divided by the initial or total concentration of HA times 100. Right? So as the strength of our acid increases, we're going to get this relationship here. So HA is pretty simple, straightforward. We can also then talk about bases. If we have a base reacting, we're not talking about the equilibrium expression that we come up with isn't for an acid, it's for a base. So we will talk about Kb. Very same thing, just like before. As the Kb goes up, the strength of the acid goes down. Or it's up, excuse me. Up and up. So Kb value gets closer to 1, the strength of that acid gets higher. And we're going to solve these the very same way, except for the products are, instead of being some ion and H plus, it's going to be an ion and OH minus. So then we can go back and calculate H plus from those. Right? The process is very simple. In fact, it's the exact same when we're talking about acids and bases as when we talked about equilibrium expressions or equilibrium in general. The only thing is we have to now be aware, are we talking about an acid or a base, and how does that relate to the information we want in the problem? We get plenty of practice in this in the activities in lecture, so we're not even going to go through an example here. Right? It's the same process as all the other equilibriums, and we're going to treat it such. We just have to be aware of what the equilibrium is and how does that relate to the answer that we want.